Why? The reason is the optimizations are applied in such a manner that it will be altering the particular result. So where exactly it is depending is nothing but it is again dependent on how the optimizations are applied at architecture. That is the column measure. The third one is type. I will show you. So this is the row measure. You can see I, J, K, result of A of I, J is equal to result of A of I, J plus mat 1 I, K multiplied by mat 2 K, J. This we used to write, sir. Matrix multiply सगळ्यांनी first year C मध्ये केले. Make sense? You can ask one more quick question, sir. Why are you taking matrix multiply example only? Because measure of the things, the phenomena that are massively parallel in nature. Satellite image processing, weather forecasting, small scale weather forecasting. What do you process? The satellite image. Can you fit image in matrix form? Yes. Seismic wave processing. Seismic wave processing. Can you just put that particular one? Yes. Then
the particular, what we can say, the particular part of drug discovery analysis, you can take vectorized data. So whenever such an applications are coming into picture, you can process with the way. Hence we are taking the basic example as matrix multiply. So this is the row measure. Now you carefully observe, after this we can have the strength, matrix and key sites. A sequentially, B column wise, suboptimal due to repeated access to B's columns. Okay. Column measure, you can go back. Here it was I, sir, right? It was I in row measure. Now we are reversing it. We are J, reversing the loop. J loop we are bringing first. Then we are bringing I and K. And the matrix multiply equation is remaining as it is. Make sense? So when I say it is happening column measure, the weakness is that 50 to 70% slower than row measure. But again it is on some kind of architectures, not all processors. Then poor L1 hit rates and frequent DRAM accesses. Perf matrix, high cache misses 40 to 60, LLC, that's so, last level cache, that is nothing but the L3. And low IPC due to memory stalls. Instructions, okay, so the particular instruction per cycle, IPC. So key issue, stride accesses A, jumps between rows, causes cache thrashing. So as I told, in column, there is low probability of having adjacent memory location elements. If it is not there, throw that block, bring the desired one. Again, access few are not there, again throw that block, again bring the desired one. What will happen in this? The block evictions will be more. Evictions, what is the block eviction? Whenever certain thing is not needed, but new need to be brought in that place, eviction will take place. It is a kind of replacement. What strategy you apply, that will work hand in hand. But if you are throwing back, evicting, what will happen? We need to bear the wasting clock cycles. So in that case, the particular cache thrashing, no reuse of B of Kj within inner loops and only relevant for column measure storage. So as I told, by default, Fortran is column measure. So there you can just have such a kind of access. Another thing, tiling. So may I ask, what is the limitation of the memory subsystem that is available on chip? What is the limitation? Capacity is low. L1 single digit MB nowadays, I am saying. Earlier it was 1 digit KBs. L2 single digit MB greater than L1. This is either single digit MB or double digit MB. So typically 8 to 12 MB of LLC. As the size increases, naturally area increases and cost increases on chip. So if it is so, there is a limited capacity on chip. So what will happen? For example, sir, you are saying you are taking matrix multiply example, take it 1024 by 1024. Okay, agree. So certainly we can accommodate some things at one level. But what if I am processing one particular satellite image that is of capacity say 1.5 to 2 GB? That's a matrix kiti mota hoil. How much larger it will be? Is it possible to accommodate all entire row or column elements at a moment at a certain space? Somewhat troublesome. So when I say in such situation I need to tackle and apply some kind of optimization, there tiling or blocking concept come into picture. So that is in architectural cache optimization terminology, advanced cache level optimization referred to compiler. So advanced optimization of one of the 10 optimizations, compiler based optimizations, what you do, you just divide the entire matrix into small tile size. So the tile size is multiple of 2, 4, 8, 16, 32, 64. I brought all tile size examples. Then you can just chosen based on the target CPU cache size. As I told, there is a upper limit on chip memory hierarchy. So when it can be performed on any one of the 3 loops IJK in or any combination balance between locality of A, B, C. Effective tile size selection and loop nesting order are crucial to performance and may vary depending upon hardware architecture, means processor to processor implementation. So when I say if it is so, the picture is like this. So instead of having entire IJK as it is, you divide it into such small tiles, small tiles, and process this much only. Process this much only, so that there will not be having any concern about what capacity of on-chip cache you are holding. There will not be any concern. So take this much process. If it is so that several partial sums are once done for a whole tile until we are done up with the entire corner. So likewise it will go and finally it will just finish up with that particular tile. So in terminology of advanced optimizations, it is known as blocking factor. So that blocking factor we need to choose in a certain smarter ways, in a such a smarter way that it must give the optimized execution time for the said problem statement. So tile code structure, instead of writing certainly, this is the tile size. So we wrote it in generic manner. When we took row measure access, column measure access. Here we are adding the tile size, j is equal to j plus tile size, j plus equal to the particular one, shorthand. Performance benefits of tiling. Tiling achieves superior cache efficiency by maximizing the data reuse and reusing the working set size per loop iteration. So among all implementations, the tile approach delivers the best runtime performance over column measure and row measure implementations. So definitely whatever you are using as a reverting loops, instead of row measure you are reverting it as a column measure, tiling will outperform for sure. And it makes the preferred method for high performance matrix multiplication on modern CPUs. I will show it. Okay, so let me go back to the examples now. So here I will show recent the tiled approach, and I have the compiled versions of tile. So before I move, I will show you the particular code of gedit via the gedit. Gedit will take tile tile 8 .c. So you can see the particular code. So we have written up a function that uses the tile size, and the tile size is 8 here. Okay, and we are taking the particular matrices of size 1024 by 1024, rows, columns, rows of A, rows of B, column of A, column. So both the matrices are of size 1024 by 1024. We have taken certainly higher range, higher capacity matrices. If you done up with this one, rest of the thing that will call the function that is written here in the particular what we can say main function, and it will just go up with computing that one. So when I say I need to just check it up with, so we can just give. So just concentrate how we are running it with perf tool. Perf tool, yeah, perf space stat space -e. Stat gives us the statistics of the events. -e stands for your events. Events might be anything, hardware events, software events. We are looking it into instructions, how many instructions are required, CPU cycles, then cache references and cache misses. And space dot slash underscore tile underscore 8. That is nothing but the executable one. That uses the tile size of 8. So if I enter, okay, I need to make this one first. Paranoid. So it has started running with 8 tile. Now you can see how the result is getting displayed. We are using the tile size as 8. We are not processing the entire matrix. Okay. So whatever 1024 by 1024, we are getting 8 by 8. That many number of elements only, and we are processing. That no need to have deal with or concern about the cache capacity on chip. Now you see, sir, these many are the instructions, these many are the CPU cycles, these many are the entire cache references, and out of these 64 lakhs 1955 are the cache misses. That cache misses are 10.67% of the all cache references which are mentioned here on the top. Now if it is so, it is taking 8.588 for something seconds time elapsed. Out of that 8.57 is user and the next one is system, as I mentioned in morning class. Now this is with respect to your tile size 8. That tile size if you move from 8 to 16, what is the difference, sir? Whether execution time is dropped. Instead of 8.57, if you 8.58 abruptly you see here itself, it is giving as 8.33. Okay. Next to that, I will make it 32. Eight point zero eight. 8.08, 8.58, 8.33, 8.08. What is our job? To select the best out of these as a tiling factor or tile or blocking factor, tile size or blocking factor, so that the optimized time should be just match. So, how many of you have done P threads or just threading in Java somewhere? Okay, so Java or C? Java. C मध्ये कोणी केलेत? Can I ask you what is a hurdle at the time of implementing P threads? You can assign to each thread a separate task. But what is the hurdle? If I have large scale application development, do I prefer to use P threads? Where lines of code is 10,000 plus. Is it okay, worth to use P threads? Reason? That need to be taken care by programmer. First thing. That is explicitly getting taken care by your OpenMP clauses. That sir will teach you now. Okay, that's why we are moving from this to this. Likewise, yet another thing is there in picture. So there is a thread creation and destroying overhead. That is second. And third, whenever I am saying, sir, I need to assign some task, synchronization is there and everything. Is it the case if you are doubling the number of threads every time, 2 threads, 4 threads, 8 threads, 16 threads, your execution time is dropping? Huh? No. The answer is no. Every time if you are increasing, the particular execution time is not getting dropped. At a certain moment, the thread overhead will be more. Hence, the execution time suddenly increases. So, when you need to choose the particular number of thread for your application, how it need to be mapped. So, there is a golden middle you are supposed to select and go accordingly, whichever particular tile size or blocking factor that is supposed to be set. So this is known as one of the 10 advanced compiler based optimizations. You can refer for this Hennessy Patterson Computer Architecture 5th edition, chapter 2, memory hierarchy. So in that, the particular 8, 9 something optimization it is given, you are inversing the loop and applying tile or blocking factor. So you need to keep a concentration that when the blocking factor is getting double, it's not every time for your architecture that your execution time is going to be decreased. You need to select the appropriate one for your size and the particular set of the program. That is one thing. So this is tiling. As I am, wait, is it getting connected? Okay, till that I will show like that only. So the second thing is row wise access. You can give perf start for that one. So you can see, observe, is it visible to all of you? Or shall I make it somewhat? Is it visible now? Per space stat space -e instructions, comma, there is no space after comma, CPU cycles, comma, cache references, comma, cache misses, space, the particular executable that uses row measure approach, the navy that we used to do every time, usually. Okay, so when I am doing this one, the executable I am feeding it to perf tool to show few hardware events, statistics, it will just display certain things, whatever I am asking to it. So you can observe now, these many instructions we need, and what is given, sir? 2.53 instructions per cycle. Instructions per cycle. So as we know well aware about, this is a superscalar. On the top of it, we have hardware-based multi-threading approaches, SMT, simultaneous multi-threading, that is a hardware-based approach. And again, what we have is nothing but a multi-issue processor. What is a multi-issue processor? What is a multi-issue processor? Single issue versus multi-issue. In a clock cycle, you are giving multiple instructions. Not for execution directly, we can say, we are issuing the instructions per clock cycle more than one. So how many issue your Intel Core i7? 4 issue. In single clock cycle, you are issuing 4 instructions. Issuing. I am not saying decoding, executing or certain else. Just issuing. How many are getting issued? 4. So likewise, 2.53 instructions per cycle. Then these many cache references as total. Out of that, these many cache misses. 3.88 of all cache references. And the time is 8.5686. Now let us move to the column wise. These all are getting applied to 1024 by 1024 two matrices. Everywhere the size of matrices remains same. So you can see now, in column wise the thing is decreased. But what I said in PPT, row measure is better in context of cache misses and execution time. But what I am using, mine is AMD Ryzen. So it is again depending upon how optimizations, prefetchings of data, how smartly the particular data is getting tackled, that and all things, depending upon that, it is giving a reverse result. I am willing to show it on my own machine. It is not getting logged in. Any desk like a problem, madam? And one more thing I am willing to show from there. So please give me a couple of minutes. I will restart. I will just try to get it from Windows. हां हां
आमच्याकडे पॉलिसी आहे त्याच्यामुळे
मी माझा डेटा घेतो 2 मिनिट थांबा 2च मिनिटं मला एक एक्झिक्युशन दाखवायचं त्यांना एकदा स्पीडअप दाखवायचं आहे फक्त बस झालं दॅट्स इट कारण माझ्याकडं क्वाड्रोपी 1000चा GPU आहे त्याच्यावर एक प्रोग्राम केला आहे तो स्पीडअप कसं नाही मी माझं येईल ना यायला तर पाहिजे Yeah, we are already in. So, is it visible? This is my own system where the Intel Xeon processor is there in picture. So, if I do the same perf stat, yeah. Is it visible? So, I will do row wise and column wise first. Okay. So, this is row wise as we did earlier. So, you can watch the data now 5.58759 some seconds time elapsed. Okay. Now, next to that cache misses are 357.01.031 likewise. Now, column wise we will go. So, you can just see column wise it is showing again less over here. So, 5.58 and 4.8. Okay. So, the particular misses are increased. Likewise, the same to the particular AMD processor. Okay. So, this is the Xeon one. But you just switch back to the older versions of the processor. Somewhat 5-6 years back, you will able to see the particular misses are more and the particular number of seconds time elapsed that are more in context of execution with respect to the column wise accesses. Okay, now here smartly the things are optimized. It is showing that the column wise accesses are outperforming the row wise. Okay, so that is one thing. Now next to this, the last one. So we have with us NVIDIA DGX GPU, and if you just see do NVIDIA SMI, you are able to see 4 Volta 100 cards are there in it. So that consists of this particular, and the utilization is nothing. So if I do CD and if I just do ./mm, so mm.cu is a matrix multiply program that is done by using CUDA program. The kernel function is written. So what used to happen in general context, if this is a host and this is a device, so the concept is not discrete now, it is integrated on the same board. They are sharing the same RAM pool, but for sake of understanding we used to say it is having its own RAM and it is also having its old RAM. So in 3 generic steps, what you are supposed to do, transfer the data from this RAM to this RAM, then second step, let the device execute the code, what it is supposed to perform, that compute intensive task. And in third generic step, write the whichever cache data back to RAM of the host. likewise the thing will happen. So if I just execute the particular code of something by something, so what is the speed up, sir? Performance of older to the performance of newer. Okay, without enhancement to the enhancement. Likewise, we observe the speed up. So what we can write is nothing but dot slash mm, for example. So it will ask you the size. So I will just somewhat make it bigger. It will ask you the size. So we'll just take 500 by 500 and 500. So I, j and k. So you just see how much thing is there. GPU is taking 1.17 something millisecond. The CPU is taking 520 milliseconds. So that CPU is itself again Xeon Gold class architecture that consists of 20 physical cores. Each core is supported by 2 hardware threads of implementation, logical 40 CPUs. Still it is taking that much, and your speed up is 443 dot something. Likewise, if I go another version, 1000 by 1000. Immediately GPU 2.421280 millisecond, CPU 4155 dot something. The speed up is this by this 1716 dot something. The matrix of same size. So enter the values of I, j, k, you will get the result. Likewise, I can do another for 5000. So GPU will give immediately, but CQ I don't know, we need to wait. So likewise the scenario. For 5000 by 5000, it is taking 1.109 dot something millisecond, and this will continue. I will send you the screenshot. Okay? Done, sir. Thanks a lot.
It is because metric multiple is a concurrent activity, so every row, every column, that is one thread it will execute. That's why GPU will be performant. But when we have to give the sequential, all your processor will be doing. That's why we convert. So that is we say that metric multiplication we have to do the row major wise. But some application it is written for column. So this is a better example that we say that metric row wise, every row,
Every column. Yeah.
That's why it will give the minimum.
Yes. And again, it is depending upon how architectural level optimizations architects have achieved. That's why older generation i3, i5, i7 are giving different result to us, and whichever new generations are there, along with again AMD Ryzen, that are giving different results. Okay. So thanks a lot. That's all from my side.
Amit sir, can we, it related, it is a speed up. Can we elaborate with the cost optimal solution related some algorithm? When we say that any algorithm we have to perform, no? So
Yeah.
we have to find the cost optimal solution that this algorithm we have to perform. Can, I'm not asking with catchy related, I'm asking with the programming perspective.
Yeah, actually, that goes towards your parallel algorithm developments
Yeah.
and their complexity classes. So perfectly, I didn't work a lot because my research go towards cache and related optimizations, hardware related optimizations, and particularly how to improve the performance of cache subsystem is the concern. So we'll have to check up with the particular part of how we are developing or giving an idea for parallel algorithmic solutions and its complexity classes, how that things are being. Or some way you can see if you are willing to give some permanent solution to few kind of problems, then in that context some proof of concepts. Likewise. Yeah, definitely the concern is absolutely correct, sir, because one of the factors that is affecting performance. Again, so that's why what is getting affected by algorithm is nothing but your instruction count first.
So that's why parallel computing we have to do the minimum processor, that minimum communication time.
Yeah, and that overhead must be also addressed. That's why in multi-cores also, sir, there are almost 13 to 14 optimizations are applied. One of the solution is parallel algorithmic solution that makes use of overhead. So how you develop using tasks, divide and conquer manner, either quick sort based algorithm or merge sort based algorithm, like this. So this is one of them. Absolutely, agree upon this. Okay, thanks a lot. This all codes the self-explanatory manual of per installation steps and the particular PDF दिलेला जातं PPT. The things will be given at the reading response. नाही नाही काहीतरी राहिलं नाही आज झोपायचं करतो.
So, on behalf of Sardar Patel Institute of Technology Computing Department, Principles of Engineering, and C.I.T, right? I thank personally Dr. Amit Joshi sir for giving me a valuable session, insightful session on performance profiling and CUDA programming. So, thank you so much, sir. Definitely, this session is insightful and it will be helpful for all the participants. Now, I request our Dean Administration and FSC, Dr. Sudhir Dhage sir, please, as a token of appreciation, give a memento and letter of appreciation to Dr. Amit Joshi sir. Amit sir, thank you so much for giving your valuable time. Very nice session. Breathe. Okay, so next up we'll have none other than our own very Professor Mr. Pramod Bede, Dr. Pramod Bede. A little about him before he comes up and gives his speech. He did his bachelor's from Ume University 2011, his master's in 2014, and he completed his PhD just a year ago in 2024, right here from S.P.I.T. He has published more than 3 papers and gotten awards for about 2 of them. Yeah, and his research interests mainly include data mining, data analytics, NLPs, and network mining. And he has been doing FDPs for the. He has done more than 15 FDPs and has attended more than 30 workshops.
He's also a he's also a member of Computer Society of India, Indian Society of Technical Education, and yeah, sir. I would like to give the stage to you.
ठीक है ना? आवाज अगर बढ़ेगा तो बोलना मेरा, क्योंकि आवाज ठीक है। ओपन करो, पीपीटी लगाओ जल्दी।
सिस्टम लागणार आहे लिनक्सची
हां हां,
तर मग ही
नाही इकडे आहे, याच्या लॅपटॉपमध्ये आहे सर, काही प्रॉब्लेम नाही.
डेस्कटॉप
Yes. Okay. So post lunch session, last session. So I was supposed to start early morning, but due to some adjustment, I'm starting now. Now we PPT starting वाला. Okay. Fine. So if you wanted to do hands-on along with me, right, you can open Linux, right? Already GCC compiler is installed by all volunteers. I request all MTech volunteers and BTech volunteers, please just look into everyone, right? So if they have any doubt, they can. And I already uploaded all codes on day 4 drive. Okay? Day 4 drive, I have uploaded all the codes. PPTs I will be sending after the session. Fine? So let's start with today's session. So before starting with, so basically what I'm going to cover, I'm going to cover about OpenMP, MPI, and we'll see some codes on OpenMP and MPI. We'll start from basics and then we'll proceed with some advanced topics like metric addition, quick sort, right? Odd and even numbers, right? So that we'll be looking into it. Fine? Okay. So OpenMP sessions are covered on day 1, MPI sessions covered yesterday, right? So let's start with a quick revision, right? So I want 4 volunteers from your side. 4 volunteers from your side. Please hurry up, don't waste time. Any 4 volunteers? सबको आना पड़ेगा because we are going to perform 3-4 activities.
PPT द्या तिथे इथे सर लावाल यूट्यूबला स्ट्रीमिंगला.
नाही हा इथे PPTs होणार नाही मी 5 मिनिटासाठी I will.
मला जर दाखवायचं असेल स्ट्रीमिंगमध्ये दाखवायचं असेल तर
स्ट्रीमिंगमध्ये होतंय ना काय?
नाही हे दिसत नाही ना त्याच्यात.
अरे मी ओपन करणार आहे 2 मिनिट या
तसं इथे जरी दाखवलं ना तर कॅमेराने कॅच होत नाही ते. कॅमेराने दिसत नाही.
क्या?
सेम PPT आहे ना ते ह्याच्यात द्या.
हाँ ओके PPT देना उसको सब. या okay, so please hurry up to 4 volunteers. Anyone can come. Yeah, hurry up please. कोड्स नहीं, सिर्फ PPT. एक कोड्स भी चाहिए क्या जो टेक्स्ट एडिटर में रहेगा? So basically, even though there are 2 partitions of this whiteboard, assume this is one for this activity, right? Yes, so please, madam. Yeah. So 4 at 4 corners. So you please stand here. आप लोग आ जाओ. मैडम आपको ऊपर करना है. क्या करना है? सिर्फ आपको सर्कल करना है. मैं जब तक आपको स्टॉप नहीं बोलूँगा आपको सर्कल करते रहना है. Yeah, you do down. सर तुम्ही या साइड ले आया. सर तुम्ही हा पुढे कर केलं तरी चालते काही प्रॉब्लेम नाही. दिसेल असं करा. ओके स्टार्ट. एव्हरीवन प्लीज वॉच. I will ask some questions. You have to answer to my questions. Okay. So basically, if you are there is one whiteboard, right, and 4 different peoples, right, using that whiteboard, they are doing some work, right.
That work may be anything. Fine. Okay, stop. Thank you. So, what is this? Can anyone tell me? What is this? Sorry? Circle तो मुझे पता है. Think logical. जहाँ पे space मिला है, okay. Okay. Okay, thank you sir. You please stand you. Yeah. Resource sharing. Repeating similar tasks. Okay. They may be they can do anything. मैंने उनको सिर्फ circle निकालने के लिए बोला. So that's the reason they were making circle, right? Parallel processing, right? But there are models of parallel processing. Which model is this? Shared memory, OpenMP, open multiprocessing, right? Wherein there is one memory. This is nothing but a memory, right? And this all are nothing but different processes, threads. Thread 1, thread 2, thread 3 and thread 4. And these 4 threads were doing some work on the shared memory. This is shared memory, right? This is the shared memory and they were using this memory. So that is what OpenMP is, open multiprocessing, right? So why we call it as open multiprocessing? You can please stand, sit down please. Okay, so this is called as OpenMP. क्या बोलते हैं इसको? OpenMP, when any different processes or threads using the shared devices, right, using shared memory, right, and they are performing with the help of different threads, right, it is called as open multiprocessing. So it's a standard, right? Any company can come up with their own implementation and they can design their own OpenMP programming model, right? So there are various companies independently designed OpenMP programming paradigm, right, for them, and it is available. You can use you can use it, right? Now, so this is all about OpenMP, where all different threads, different processes are making use of shared memory in order to do their work. बराबर है? Memory is common, right? And this all threads are using that memory, right, in order to do work. Fine. Okay. Now again, I want 4 volunteers. Please come ahead. Slide. No slide. Yeah. Any 4, please. There must be gender equality, नहीं तो वे लोग मुझे बोलेंगे सर आप. Yeah, one more please. Okay. So come up with your pad. One pad is given to you. One pad is given to you. Pen is also given, provided by us. So please come up with pad and pen and a blank page. Blank page. Okay, you have to face to all participants. Fine. Yeah, face ऐसे करना है. ओके सर, मैं अभी वापस सर्कल बोलूँगा तो अभी जो सर बोलेंगे ये तो सेम टास्क कर रहे थे. सर आपको ट्रायंगल बनाना है, मैडम आपको रेक्टेंगल बनाना है, मैडम आपको सर्कल, और सर फेवरेट शेप सिलेंडर. स्टार. ओके, सो योर स्टार्ट. सबको दिखना चाहिए सर, आपके लिए नहीं. हाँ, ऐसा. ओके, सो प्लीज स्टार्ट. Okay, so what is happening here? Parallel processing. Sorry? Unique memory. Independent memory. Distributed memory. Okay? Okay, so which type of programming model is this? MPI. Message Passing Interface. Stop, please stop. Madam ने तो बहुत अच्छा डिजाइन. Madam, but unfortunately we are not here for a competition. Okay? Yeah. So just show your, yeah, please. So see, this is nothing but one memory, separate memory, and these all are nothing but processes. Process 1. So when we talk about MPI, okay, we call it as a processes, and when we talk about OpenMP, it's all about threads. Okay, OpenMP we call it as threads, and when we talk about MPI, we call it as different